Okay, welcome everybody. Thanks for being here. Today we're very happy to have Wei-yao from Los Alamos National Lab. He's currently a director postdoctoral fellow there, and he will join CCNU as assistant professor, right?
I suppose so.
Hopefully soon. Wei-yao was a postdoc here in this group, so many of you have seen him before. He got his PhD from Duke University in 2019. Then he spent 2 years here, kind of here because of the pandemic. And as I said, he's a postdoc in Los Alamos right now. And his work focuses on studying nuclear dynamics in high density or high energy environments like quark-gluon plasma, but also how jets propagate through cold nuclear matter like collision at EAC. And today he's going to tell us about Parton shower and cold nuclear matter, and in particular the Monte Carlo site and the theory developments. So please, go ahead.
Yeah, thank you. I never sent you my bio, but you got some of my information very accurately. Yeah, thank you. Thanks for this opportunity to talk at the HIT seminar again. This talk is about Parton shower, especially in the environment of nuclear matter that you can get in electron nucleus collisions. And this talk will be based essentially on 2 recent papers that we put on arXiv. One that I started when I was here with Xinyan to develop the eHIJING Monte Carlo model to study this problem. Another is a fairly recent one that I had at Los Alamos. It's a more theory-focused, but I think this paper will really help us to understand why we can build the event generator in the way we do. So I think it's very nice to talk about this work in this talk. So as the background, we're primarily interested in all the nuclear effects if we can perform this very precise deep inelastic scattering experiment on nuclear target. And we know that in a nucleus, you can have all kinds of nuclear impacts, including, for example, the most important one, of course, the non-productive input, how the nuclear structures, all those short-range correlations affect the DIS process, and how are the nuclear Parton distributions behave differently in nuclear environment versus the proton. For example, there are also recent extractions of the transverse momentum dependent PDF in atomic nucleus. Another big class of effects, let's call it dynamical effects. So these are the effects that can be process dependent. It depends on how you trigger this your probe to probe the matters. For example, these dynamical effects can include dynamical shadowing, that the hard process may involve more than 1 nucleons coherently, and how this Parton shower develops inside the medium, or this multiple collisions that may affect the Parton shower development. And there, of course, in the final state could be hadronic interactions, and the target may have some additional dynamics. And all of this can be process dependent, and you have to, in principle, have to study them case by case. But in the presence of a larger separation of scale, I will try to convince you that there's still a certain region of phase space, quite important region of phase space, very relevant for Parton shower, that even the shower in the medium may display some universal behavior. And to understand the Parton dynamics is actually quite important because, as you will see, the measurement will always involve both of these effects. It is really after you understand the dynamical effects that we can properly define what are the NP input we want to determine from these experiments. Okay, so throughout the talk, most of our discussion will happen in the rest frame of the nucleus. So the rest frame, the nucleus is a sphere, and you have a virtual photon coming in, now called quark, for example, in this leading order process, and then it undergoes some subsequent dynamics. And then this, there's an equal sign is over here, is the semi-inclusive DIS cross sections. And in the DIS limit, this is factorized into a hard cross section the PDF, and this is the fragmentation functions for measuring one hadrons. And we specifically focus on the DAS limit, where you trigger on a very large Q-square events and focus on the large B regions. And there are reasons why we focus on this region is that these are the necessary criteria that this hard production is localized relative to the whole size of the nucleus. For example, you can compute what are the coherence time, either longitudinally or transversely of this hard process. Transversely, the hard process only extends a very confined region of 1 over Q, and you can make it arbitrarily large by choosing a Q such that it is inside the nucleus. But in the longitudinal direction, because of the whole process's boost, its coherent time is actually the energy of the photon divided by Q squared. And if you want this to be inside the nucleus, you have to put some limits on the Bjorken X that you're measuring. For example, we'll primarily focus on X greater than 0.01, such that you can still meaningfully talk about the hard production happens somewhere inside the nucleus and then travels for a given path length in the medium. Okay, and then in the final state, that's where the interesting stuff happens, is that you can have multiple collisions between the jet parton and the constituents of the nucleus. And for this type of interaction of a relatively a relativistic parton interacting with the medium, the dominant mode that transfer the momentum are the so-called global region, where the gluons are highly off-shell and this transverse and carries very little longitudinal momentum of the nucleus, and its main effect is to kick the jet parton in the transverse directions. And now it depends on which region you are focusing, you can get all kinds of effects. For example, you can consider some of these collisions may be very close to these hard production vertices, and they will actually contribute to the coherent power corrections of the DAS cross-section and leads to dynamical shadowing. Or another way is that you don't compute it as the dynamical processes, but parameterize this effect into the nuclear PDF, which is right now most event generators use this approach. Another effect is that for most of these collisions, they are not actually really coherent with the hard process. They are incoherent collisions and contribute to the transverse momentum broadenings and will induce extra radiations from the part.
I have a naive question actually on the previous slide. The differential cross-section that you have there is not differential in PT, or is it because it's not?
It's just for demonstration of what pieces we need. In principle, you can write this full differential in PT, then it will be a transverse momentum dependent.
My question is, if can PT provide you a harder scale that localizes the interaction? So maybe Q is not very large, but PT is large enough.
That's a good point. So PT is indeed an additional handle, but I think in this DS region, Q is already the hardest scale.
Yeah, what I was thinking is, I know it might go beyond, but let's say you have an ultra-peripheral collision, where one of the ions acts as a photon source, but the photons are real. So the Q is very small, but I wonder if this could be adapted.
In principle, yes, you can always select. So in the also ultra-peripheral collision, you can always select it, for example, in the backward region or in the middle rapidity, a very high PT process. Then that would be similar to a localized production.
Okay.
Some question. For the notation, what I and J?
Oh, sorry. This I is just which type of parton you get from the nucleus, like quark or gluon's label. And J is that in the final state, which quark is fragmenting into the hadron you observe.
Oh, okay.
And then sum over all channels.
And the slash A and the slash.
Oh, it just means a parton from a nucleus of mass number A.
Oh.
This means a hadron from parton J.
Okay.
Okay. And usually people try to quantify this amount of transverse momentum broadening and try to attribute all this effect into this important transport parameter of the cold nuclear matter. That's the jet transport parameter. Q hat, it measures on average how many transverse momentum broadening the root mean square, the average square momentum broadening you can get per unit length inside the nucleus. And that's how we usually try to quantify how large this number is to characterize this transport property of a nucleus. And in addition to the collisions, as I said, this additional broadening will also induce more radiations from the parton and will also modify the longitudinal structure of the fragmentation function. And this is indeed been observed many years ago since actually since the EMC collaborations in 1991, that you observe that in the nuclear environment, the fragmentation functions, if you take the ratios of the fragmentation function measured in EA divided by electron deuteron as the baseline, the fragmentation function is strongly suppressed as a function of the momentum fraction that the hadron carries. Of course, you also have PT broadening, so you have the low PT regions, hadron is depleted, and some of them are transferred to the higher PT region. And these are actually quite important. It means that even though, of course, all of these corrections will depend on your cold nuclear matter transport parameter, but how do you really relate those parameters to the final observables? You have to take into radiative corrections into account, especially those medium-induced radiations and how they fragment in the cold nuclear matter environments. So for the rest of the talk, I will first introduce you this eHIJING Monte Carlo model that we developed, and to give you the idea of how these different pieces goes into a simulation of what happens in electronuclear solutions. And then in the second part, if I have time, I will try to also develop some analytical understanding of why this event generator can be developed in this way. Okay. So this is the typical structure of event generation. You usually started with two beams. In this case, on one side is the lepton, another side is a proton or a nucleus, and then they're characterized by their nuclear PDF or proton PDF. And then you trigger a hard process at a large Q square. And if you're in the vacuum, then this process will undergo vacuum emissions. That's usually handled by this, for example, in P8 event generation, handled by this PT-ordered Parton shower that closely simulates what you expected for example, inclusively a D-glap evolution would do. And the key input will be the QCD splitting functions. And then after that, the event generator will collect all the Parton showers, partons from the Parton shower, and also the nucleon remnants, because that's the whole system, which is color neutral. And they will connect strings between these remnants and among the Parton showers to perform hadronization using, for example, the actually very well tested long string hadronization model. If you focus on these two red boxes over here, that's how we include medium corrections. The center of this is, of course, those multiple collisions. It's that parameterize how the jet will collide with those very small X gluons inside the medium. And then they will have two impacts. One is that they will recoil on the jet partons and also create more nuclear remnants, because this secondary interactions usually happens with independent nucleons, and then will recoil another nuclear remnants into the system. And also it will modify the splitting functions. And eventually we will put all together all of this modified Parton shower and modified bunch of remnants together and again perform long string hadronization. I will go into each of these blocks individually. So the key, the center of this modification is that we have to figure out a way to model what happens between jet and the medium. And one of these such models is that you can relate the cross sections for a jet to collide ones with the medium constituents to the unintegrated gluon distributions, or up to some factors related to the TMD distribution of gluons at very small x in the nucleus. So basically, the cross-section for this jet parton to deflected at certain transverse momentum is related to the coupling constant, some color factors, the unintegrated gluon distribution divided by KT squared. And now we will come up with a model, actually motivated by the saturation motivated parameterization for the unintegrated gluon distribution. Is that at a very large KT, you will recover the perturbative Coulomb tail. So if you neglect whatever that's not proportional to KT in the denominator and plug it back in, then you will have the cross-section proportional to 1 over KT to the 4th. That's the Coulomb cross-section. While the infrared are screened by saturation scale to make this cross-section, actually to make the total momentum brought infinite. And this saturation scale is computed self-consistently by requiring that this scale is actually proportional to the unit area density of the gluon contained in this parameterized gluon distribution function. And on the right-hand side, I showed you what this saturation scale looks like as a function of xb for this jet quenching process. Here we throw in some parameters, which are actually the parameters we will use for calculations later. Is that this density will grow with some power at smaller x, which we choose to be minus 2.25. And when x is very close to 1, is also suppressed to reflect that you don't have that much gluon at large x. And that's what you get. So you have a saturation scale that's maybe 1 GeV for a typical large nucleus at x from 0.1 to 0.01. And as you can see, this saturation scale is counting how many transverse momentum you can get from this unintegrated gluon distribution. So it's also closely related to the jet transport parameter that we defined earlier.
Oh, we have a
Yes.
quick question on that slide. So there, that integration sign is starting from lambda square. What is that lambda?
Lambda cubes, some other non-perturbative cutoff. Of course, in this case, you can extend it to 0, because for this particular parameterization, it doesn't diverge anymore. But for general parameterization, in principle, you need to implement lower cutoff.
To avoid divergence.
Yes.
Okay, I see. Thank you.
What is the rho n?
Oh, sorry. This rho n is actually the thickness. It's the nucleon density times the path length.
And so the saturation scale grows with precisely that power of lambda?
At very small
At
x,
very
yes.
small x.
A quick question. So if you integrate start with 0, will it be loud divergent? So you have a
For this parameterization, no.
No.
Like if you plug in this over here, in this case, all the divergence is already screened by this saturation scale.
yeah, but the cross section in the first one, the d sigma g
Yes.
cross
The
section is
cross-section, yes.
is
The number of collisions will have this log divergence because, of course, number of collisions is not a very well-defined quantity, but the total transverse momentum broadening should be more well-defined. So in this case, if you compute a momentum scale, that's free from log divergence, but if you count how many how many collisions it happens, it does diverge with this lower cutoff.
okay. So sigma g can be divergent, right?
Yes.
Okay.
Another question. So for mean of the self-consistently means on the left-hand side, there's a QS, and on the right-hand
Yes.
side, it's also
QS also enters.
So you solve that numerically, or
Yeah, numerically you can solve it.
okay.
Okay. And this scale is actually closely related to the jet transport parameter because in the transverse direction, this is the only momentum scale. And if you use this cross-section to compute what are the average transverse momentum broadening, you will find that the jet transport parameter is just up to some color factors, the saturation scale divided by its path length. So this is the jet transport parameter for quark in units of GeV squared per Fermi. And for example, at x equals to 0.1, you will roughly get 0.1 GeV squared of Born broadening for every Fermi you traveled in nuclear matter. Okay, so that's the key building block. And then there is another very important theoretical input, is how those multiple collisions modifies the QCD split functions. This has been recently revisited in this generalized higher twist framework by Xinyan and his student Yuan Yuan in this paper from last year. In this case, at leading twist, the radiative correction is that after the hard process, the parton can radiate once to create two particle final states. At a higher twist, you consider there's additional multiple collisions with the medium, and then this will contribute another piece to the splitting function. So we call it at this level twist 4, where we'll consider how one more collisions modifies, how one more interactions modify the splitting function. The form is actually quite involved, and there are some, of course, approximations that goes into it. For example, when you have this twist 4 contributions, it's actually you are measuring some 4-point matrix element of the nucleus. And for a large nucleus, if you only focus on the nuclear enhanced parts, you can actually factorize it into two-point functions, and one of them will become the quark distribution function, and the other one will become that unintegrated gluon distributions. And the splitting function will have several pieces, but we will drop several. One is suppressed by 1 over NC squared, so only naturally it will be only like one tenth of other terms. Another one is not even enhanced by the medium, and is only power suppressed by the ultraviolet cutoff. So the main contributions is in the middle. And to just see the physics more clearly, we will further make the approximation, which is the soft gluon approximation. So after you make the approximation that medium-induced radiations are predominantly soft gluons, then that whole expression becomes this very compact formula for the modified splitting functions. In these split functions, everything is still proportional to the vacuum splitting function, but now it involves the integral of where this collision happens along the path. And this whole process is actually modulated by a phase factor called the Landau-Propchunk-Migdal effect, for short LPM effect. So if you look at this phase factor, it's actually strongly suppressing radiations with long formation time. Oh, sorry, I forgot to mention that this tau f is the formation time. It roughly measures how long it takes for the two daughter partons to lose coherence. So if it takes longer, which means that they become more collinear, then this phase factor is very small. So those long formation time radiations are strongly suppressed. And here's another subtlety, is that historically when people try to use this formula, it's still quite complicated. So they perform another expansion, is that you try to focus on the twist limit, that you try to expand in powers of k over L, such that you think these multiple collisions are very soft, while the radiation is relatively hard. But back then, this expansions was performed under the integral, but the most consistent way to do it is that you perform this expansion after the integral, which actually does cause some differences. And as you can see, this is the vacuum black lines are the vacuum splitting functions, and the colored lines are vacuum plus this correction. And depending on whether you do this most consistently, especially at relatively low transverse momentum, there are quite important some log factor differences over here.
Sorry, I'm confused. When you say before or after the integral is KT integral, right? Like how do you do it after?
To do it after, in this case, you can actually shift the momentum integral. Of course, the shift is not 100% accurate because there's some boundary over here. But for this type of shift, the boundary term only, so the boundary terms are always plus something over the boundary cutoff. So if you only focus on the medium enhanced effects, you can shift it around.
If you do it after, right, then there is no longer KT, right, because it's integrated. You integrate over it.
Oh, yes. So to do it after, in this case, it becomes 1 over LT. So you have some other scale still remembered in the denominator, and then in this, after KT integration, you expand in powers 1 over LT.
Relative to what? So LT?
In this case, relative to the momentum broadly, actually. Yeah, but just bear in mind there are some differences, and for eHIJING, we actually implement both options to let you see how much differences cost in the observables.
Just a question.
Yes.
So how do people usually estimate the different, like probably systematic error from this approximation? Is there any way to?
In principle, this approximation is, if you do it consistently, it is actually consistent with the twist 4 calculation. So twist 4 calculation is only accurate to this order. But of course, if you want to estimate what are the approximation level conservative of even higher twist, hopefully I will have some time to cover that at the very end. But in principle, yes, you need to find a way to estimate.
Okay.
Okay, now you put all these pieces together. We now have we now know how we modify the splitting functions. We know how to recoil the jet transverse momentum from this extra momentum exchange between jet and medium. The next problem is how you sample multiple emissions. So in the vacuum, that we know that from a Parton at very high scale down to hybridization process at low scale, there are actually multiple emissions going on, but due to this large separation of scale. For medium, we developed this eHIJING multiple emission in a way that closely follows this modified deglap evolution picture. So the deglap evolution is usually what you have in the vacuum. You generate multiple emissions strongly ordered in the virtuality. And for the medium part, you just add this medium corrected splitting function over here, and then try to redo this this procedure to generate medium multiple emissions. Of course, it seems like a choice, but later I will show you what's the physics that actually goes into this. In addition, because usually the deglap evolution is usually have an initial condition that's fixed at, for example, 1 GeV by, for example, fitting a set of PDF or fragmentation functions, while the medium effects can be somewhat softer than that. So in this later paper, it was proposed that you first add some medium effects to the initial condition of the deglap evolution, and for the rest of the medium corrections, you include it into the modified deglap equations. So this is indeed the picture that we follow in eHIJING. So we will get this medium modified splitting. For those splittings that involves a large transverse momentum, for example, right now we choose to be larger than the saturation scale, it is added to the splitting functions inside Pythia, and then the machinery of Pythia will generate this PT ordered Parton shower. For those low virtuality Partons, low virtuality splittings, that transverse momentum are comparable or smaller than the saturation scale, we will generate this Parton shower ordered in formation time. So actually, even though I say it's a formation time, but in this case, formation time is actually just the inverse virtuality of the splitting. So it's still some virtuality order shower, but just not PT order. Okay, and then the final step is that now you have a medium modified Parton shower with a lot of additional soft gluons emitted from the system. And we also keep track of some remnants from those multiple collisions. This is, of course, another model. We consider that one multiple collisions between the jet and another nucleon will break that nucleon into a quark plus diquark pair. And we'll assign colors to the diquark pair such that you can still keep the whole system color neutral. And then we put this color neutral system again back into the PCL hydronization module to perform hydronization. Of course, there's a caveat, is that because medium emissions really generate a lot of soft stuff, and a lot of those multiple collisions can happen way below perturbation scale. So you may consider whether, in this case, a partonic picture, it still works. But of course, this is what we have right now. I think in the future, one should really consider some practices that has been done for many years in heavy ion collisions, is that for those very soft degrees of freedom that comes out from medium jet interactions, you just put them as soft energy momentum back into the system. And for example, let some multi-particle dynamics or collective dynamics to handle how this part of the energy momentum will propagate in your system. For example, in heavy ion collisions, the medium is this quark-gluon plasma, and for those medium recoils and soft emissions down to the scale of temperatures, for example, in this work, they put it back into the hydrodynamic evolution equations and let hydrodynamics to handle the plus freeze out to handle the hydronization for those part of your system. Okay, before I lost your interest, this is some results. So now you can simulate from the eHIJING framework and study how the fragmentation processes in electronucleus collisions are modified. This is the comparison of the pion fragmentation function. You measure the pion number, normalized pion number in EA collisions divided by electron deuteron. This is for, let me see, class experiments. So it's actually, I should put it over here, a 5 GeV electron beam hitting a fixed target experiment. And you can, as you can see, as you change the size of the nucleus from copper to iron and lead, the suppression gradually increases due to the increased size of the nucleus. And we actually tune the magnitude of the unintegrated gluon distribution, and therefore the magnitude of the Q-hat transport parameter.
So this is a double ratio, right?
Yeah, it's a double ratio.
So what is N and gamma?
Okay. You count the hydromultiplicity normalized by how many DIS events you trigger. So it's actually a multiplicity per event. So this is roughly the region of Q-hat that can let you describe the data you observe at class. And by the way, the blue and red curves corresponds to whether you plug in the historically approach of higher twist splitting function, or the latest, the more consistent generalized higher twist approach. They do cause some differences, but of course, because the jet transport parameter is fitted, I won't emphasize too much on these differences. They should be understood as your theoretical uncertainties. Okay, and this is the same observable, but from the Hermes experiments. So Hermes is actually a slightly higher beam energy. It's a 27.5 GeV electron hitting a fixed target. And it has a more variety of nucleus from helium, neon, krypton, and xenon. Again, as you can see with the same range of jet transport parameter, you can describe the the Z dependencies and the nuclear size dependencies fairly well. And that's the longitudinal fragmentation function. So this one is the produced hadrons, but you measure the transverse momentum relative to the hadron and see how the ratio changes with transverse momentum. This first figure is that you use the same Q hat that you fitted for the longitudinal fragmentation function, but you only include collisions without any medium-induced radiations. So you notice that actually this pure collisional processes only accounted for maybe less than half of the total momentum broadening. So by the way, it's broadening because once you have more transverse momentum given to the parton, it would deplete the distribution of hadron at lower momentum and transfer to higher momentum. So if you only have collisional processes with the same Q hat, it's only explaining part of the data. It is really the recoil from the medium-induced radiations that's accounted for almost the other half. Of course, there's still some fine-tuning that you can do, but it is enough to illustrate the point.
It looks like high twist is a little better here.
Yes, that's why I will not emphasize too much of the differences, because I mean there are many parameters that one can tune, and as you can see, there's a lot of parameters we didn't tune, like n equals to 4, lambda equals to minus 2.25, which are clearly fixed by hand.
So sorry again, what happens from the previous slide to this one? What was
the difference is the previous slides only have collisional broadening, and we turned off radiations. Mm-hmm. This one we include both collisions and medium-induced radiations. Mm-hmm. Of course, a more differential test is that you look at the Z and the PT dependencies simultaneously. So this is for all 4 nucleus, and each one of them presents as a function of PT, but divided into different bins of Z. So you are simultaneously differentiate with respect to both of them. Again, this seems fairly well. Description of the overall systematics, especially at large Z, you're more dominated by energy loss, because at large Z, a little bit of energy loss, you cannot produce hydrogen in this Z region anymore. So in this region very close to the Z equals to 1 threshold, energy loss is very important. But once you get to the intermediate or lower Z regions, you really start to see this momentum broadening start to take over. Okay, I think that's a lot of results I already showed you, and actually I do have more results, especially for those simulations at collider energies at EIC. But before that, I think we can pause and ask a few questions, a few theory questions. First of all, as you can see from the value of the jet transport parameters, the typical momentum broadening is just a few hundred MeV, which is clearly not a very large scale. But why does, for example, this medium modified Parton shower, which based on product picture gives very reasonable results? That's one question one can ask. Another question is, what is the physics behind the modified D-glab? Essentially, what are the large numbers that you are resumming in the modified D-glab? That's another question you can ask. And of course, you can even ask about uncertainties, how much uncertainty you introduce when you make these soft Coulomb approximations, and do you need to worry about twist 6, 8 contributions to the splitting functions? Of course, you can keep implement those splitting functions into the Monte Carlo and study it, but a faster way is to see if there's any analytic insights that can at least partly answer these problems, and will, of course, in turn benefits Monte Carlo developments. So that's the second part of this talk, is some work in this direction. So throughout the study of eHIJING, we're actually making a very important assumption is that at large XB, the nucleus that as you probe it is still a dilute system, and the size is not very large, so we call it a thin medium and dilute medium limit. And in the past, all of our intuitions, we have to run all those simulations or at least do numerical solutions to modify big lab equations to get insights, because the main obstacle is that there are simply too many scales for this process in the medium. For example, even at twist 4, the splitting function actually contains two scales. One is E over L, coming from the LPM effect. Another one is the screening mass. In our case, is chosen to be same as the saturation scales. So even this splitting function itself already contains two scales. You have other two scales like a high hard Q square and non-perturbative lambda QCD just from the vacuum physics. So to make some progress, we have to drop something and consider some limiting cases at large scale separations. So actually consistent with this thin and dilute medium, there is indeed a large scale separation. Is that this nu over L, the typical energy scale of where LPM effect happens, is much, much greater than all the other screening mass, including, for example, lambda QCD, saturation scale, or any other nuclear effects. Let's collectively call them C square, and we will not differentiate which one is larger within this group. We just want to make this large scale separation between nu over L and all the other rest of medium scales. And it's also consistent with this thin medium limit. Oh, by the way, this is not true if you consider the medium is dense. For example, if either Q hat is large or the path length is large, because they depend inversely on path length. So for dense limit, these scales will be reversed. And in that case, you will need a completely different picture to study the partition.
A quick question here. Then for the small nu, it will also bring that nu over L scale
Yes.
to lower.
Yes.
So okay.
So it means that, well, yeah, of course, for small nu, for example, if you produce like a 1 GeV proton in the nucleus, it's moving almost non-relativistically, right? And of course, you will have hadronic interactions. In that case, all this partonic picture will stop work.
Okay. Gotcha. Thank you.
Okay, and then, so this is the, I think, most important slides for the second half, is that now if you do this power counting in the thin and dilute medium, and you notice that there are always LPM interference there. So the LPM interference is basically that for every interaction with the medium, you accumulate a phase. And you don't want this phase to be too large such that it becomes a destructive interference. So all the modes that are sensitive to medium size, it must be that this phase is of order 1. And then this sets the power counting for the medium-induced collinear mode. So this medium-induced collinear mode has this typical momentum scaling with an invariant mass of nu over L. So this is actually a semi-hard scale for large nu and not so large medium. It can be 1 or 2 GeV, like this, for Hermit's energy. It is actually a semi-hard scale. So this is actually the reason that why there's a region of phase space you can actually apply perturbative physics in the first place, is that even though zeta square can be non-perturbative, there's a semi-hard scale in thin medium.
What is your Cassi now? What is your Cassi?
Cassi including lambda QCD, saturation scale, collectively called.
Oh, okay.
And then there's another set of mode. If you look at the figure on the right, so here basically I'm saying that the hard production happens over here, where the momentum P square is comparable to Q square. And then now all the medium physics happens along this line where P minus is comparable with 1 over L, such that LPM effect doesn't kill them. And now you have the collinear medium mode, which is where this line intersects with this semi-hard scale. And then you can go down and down until this line intersects with another medium scale, which is this C square, including the screening max and stuff. So this picture actually tells you that it's still, these different modes are separated on different mass scales, so it's still a scale evolution. But it's really because the LPM effect has to align all these medium modes along P minus equals to 1 over L. It looks like that you're getting softer and softer radiations, but that's really because of the effect of LPM effects. And now is something interesting that we start to working on, try to formally write it down, is that once you have momentum modes, two momentum modes that scale like this, where they only interact with one of the minus component, they can actually be decoupled by some decoupling transformation. And in this case, it means that in principle, you should be able to factorize these two modes. By factorizing, it means that the consequences are that when you only focus on the collinear mode, you can just drop or power expand away any small numbers of z square over this semi-hard scale. Of course, it may cause some divergences, but the factorization allows you to use RG to cure that and also perform resummations. Another important consequence is if you can actually factorize these two scales is that now it doesn't depend on what type of detailed assumptions you make to screen the divergences in this jet medium cross sections. For example, right now we use a saturation scale, or for example, Ivan will probably choose to use this static screening of the Coulomb potential. We have some other models to screen the inferred behavior. But as long as they have the perturbative tail, the form of evolution will be the same among all of these calculations. It is really where you stop the evolution and how you handle your initial condition. That's differences. That's different among different choice of the jet medium cross section. So in this picture, you can actually go ahead and get some analytical insights. Is that when you compute an L correction from the medium induced splitting functions folded with the for example a Parton spectrum. For example, that will be the initial condition of your Parton shower. And now you know that before this quantity depends on two scales, zeta square and nu over L. But now in this new picture, you can actually expand this term in terms of this small number v, and then up to some order v corrections, you can actually get a closed form of this medium corrections. And I will neglect a few details in the middle, but the bottom line is in this way, you can actually identify what are the large log being resolved in this type of calculation. It is actually the log of nu over L over z square. So in the case of this particular model, that will be this large number that being resolved. And actually, because of the medium induced radiations are often much softer than vacuum splitting, so compared to vacuum splitting, it has two additional poles to emit either very soft quark or very soft gluons. It actually has a very different form of evolution. So this evolution equation is actually not a differential integral equation like DGLAB, but actually just a PDE involving partial differential operators. And this is just for the flavor non-singulated sector. And just for this sector, you can actually arrive at an exact solution that before the evolution and after the evolution, the primary effect of the medium is just energy loss. So this is now not, so energy loss is not just a model, but it actually is the solution of the RG equation. That you simply shift the momentum fraction by this amount of energy loss, which of course proportional color factors, and integrate it over the amount of interactions you get from one scale to another. This denominator comes from the conversion, is that you quark give almost all the energies to the gluon, and then you are left with a soft quark. So it's like a loss term to the quark distribution. So overall, it's a suppression in the denominator. But it's relatively less important because for very fast change in shape, the energy loss is always very important. A little bit of energy loss, and depending on the steepness of your spectra, the RA can change a lot. Okay, but this form looks very different from Monte Carlo. Why are they the same? This is actually because in the Monte Carlo we always keep two scales, so it's not very easy to see what are the leading log structures. So here, let's do the comparison. So this is the flavor non-standard from the renormalization group approach. And here is a simplified version of the Monte Carlo of the non-singlet sector under soft gluon approximations. I will not go into the details, but in fact, if you now follow the same spirit that you only want to extract the leading log structure in E over L, you can actually eventually get this solution almost identical to the RG equation, except that the power in the denominator is a little bit off. This is just because we make the soft gluon approximation. So you're actually not describing emitting hard gluon and soft quark very well. So in this case, you directly see how much of uncertainty you may introduce when we plug in the soft gluon emission approximation. So maybe something will be should be even more suppressed if you use the exact splitting function. Okay, I'm very close to the end. So this is the results from the RG evolution approach. So it's actually provides you also quite satisfactory description of the data using a Q hat similar to what we need in, for example, in other phenomenological study, including eHIJING. But I think the point is not that we want to use this either approach to fit anything. I think the point is that now we have a series benchmark for Monte Carlo in the median, especially in this symmetry limit that we're interested in. So in principle, in the future, we can actually use this new analytical approach to benchmark implementations in event generator to achieve higher accuracy, and is importantly to define what are the accuracy we implement in the Monte Carlo. And I think that the interaction between Monte Carlo development and series developments is quite important in the future if we want this thing to be systematically improvable, to have a well-defined uncertainty, and as such. Okay, and these are the other results from eHIJING I promised you before. Is the from fixed target to collider energies, is that now you can really do this quite highly differential studies of how fragmentation functions, how transverse broadness changes in different phase space regions of X and Q square. For example, in this case, the solid line covers roughly the region of EIC. I think maybe it will cover even higher center of mass region. So this is the center of mass region, I think, for square root of S equals to 45 GeV for electron-lead collisions. I think it'll be able to cover even higher square root of S. And this lower dashed lines, this is the range from the class 12 experiment. And in the middle, that will be the range from the EIC in China, if I didn't miswrite their white paper. And now you can scan different fix different Q square region or fix different XB regions, and these 5 regions are what's shown over here. And as you can see, so now we have the semi-analytical solutions. It's very easy to understand that the energy loss is proportional to XB and inversely proportional to Q square. So you do expect that the modification is largest in this lower corner and gradually becomes smaller when I go to large Q or small XB. Similarly, you can do this for the transverse momentum spectrum modification, but in this case, it's harder to interpret the hierarchy, because even though when you go to large Q square and small x, you get a larger Q hat, but the transverse momentum spectral baseline is also changing. So right now I don't have a good intuition to explain why it all looks so similar over here. So, but one thing that is useful is that you just compute what are the average, average transverse momentum broadening of hadrons. We can average them within a certain region of the hadron's momentum fraction, and then use this information hopefully to determine the co-nuclear matter transport parameter very precisely. Again, radiative corrections is very important. Is that this green line is what you expect from pure collisional effect, and to reverse engineer the co-nuclear matter from data, you do need to take into account that the radiation corrections is also very important. Okay, that would be my summary. The first part is about the Monte Carlo development to let you see what are roughly the physical ingredients that we need to study this phenomenon in electron-ion collisions, including collisional processes and medium modified split functions. And this is now being implemented at twist 4, and with multiple emissions follows the picture of the modified Diglap equations. The second part is the theoretical understanding of why the modified Diglap evolution equation, this picture, works for this medium limit. And we actually have some analytical results that can be used for future benchmark of Monte Carlo developments. So I think all of this is actually very critical to define model accuracy and for physical extraction of transport parameters. Okay.
Thanks, Wei-yao, for the talk and for the interesting results. Do we have further questions for Wei-yao? Maybe online as well. Does anybody have any question? Oh yeah, Xiongling, go ahead.
Yeah, quick. So for slide 20, what is FO plus RG? What does FO mean? Slide 20.
That's actually that should be the. So RG is just our evolution equations solution, but you also have some finite term that's not enhanced by any law. So that's FO means this remainder of the NIO contributions.
Okay, so FO RG is more accurate than RG only, right?
In principle, yes, it includes some contribution not included in the evolution equation.
Okay, thanks.
I also have a few small questions. So I see you compared with the Parton result, like can you also compare to like K-ion, like
yes.
even separating K plus, K minus?
Yes, actually there's still some tension here.
Or protons.
Yeah, that's the PiKP. This is from eHIJING simulation. So Pi also include, so Pi minus I didn't include. So Pi minus is very close to Pi plus here. Pi zero is slightly different. What's very interesting is actually K plus K minus. Is that if you try to overlay left and right, all the pions, their separation levels are quite similar. But K plus and K minus are very different. And also there's some hint that K minus may be differently when it's very close to the strike, maybe, but of course, very large uncertainty. Using the analytical approach, we also try to use different fragmentation functions for K pi. It's total mess. Depending on what type of fragmentation functions I use, sometimes even the K plus, K minus ordering are somewhat reversed. We can double check whether we made a mistake, but I think the species dependencies are not very well understood right now. I think.
Because like in your framework, like it's mostly just like this medium induced Parton shower modification.
Yes.
In reality, there also may be like absorption or hydraulic level interaction that make the different charge different, or like the meson baryon.
Yeah, for example, if you look at the low Z region of proton antiproton, antiprotons are clearly more suppressed at low Z, and in this case, it's roughly 1 to 2 GeV antiproton in the nucleus. Maybe that's absorption.
Okay.
In fact, for that, there's one should also include the hadronic afterburner.
Right.
Means when the hadron was produced after the formation time, the hadron can also scatter inside the nucleus if they are formed inside nucleus.
Yeah.
And in particular, if you have an antiproton, the antiproton definitely will be most likely annihilated inside the nuclear matter.
Sure. Yeah.
And this is not included in the current version of
Yes.
this of eHIJING yet.
And then another maybe follow-up question. So I guess then like both the Monte Carlo and also your analytical framework can also be extended to like heavy flavor hadrons. Or that's
Yes, so we do have the plan for heavy quark in eHIJING.
Yeah.
I think for event generator, that's more straightforward. For the analytical approaches, we haven't. So maybe there's another more scale.
okay. From the mass.
Yeah.
I see.
Yeah.
But for event generation, you can always.
The other processes should be easy to implement. It just I'm not so sure how important are they, because they definitely should be suppressed, because if the energy goes higher, the annihilation, for example, the cross-section is suppressed by one of the.
But this process needs novel input. Right? It's not then you need the quark, right?
Yeah, it's
So
quark.
it's not quark.
Yeah.
It's not
First of all, you have to know what is the distribution of the quark. Right? That is okay, man. That you can model, but most likely the annihilation process is most likely suppressed by one of the the center mass energy, which
that may be important for.
is comparing to the T-channel scattering, that is most suppressed, I think. Yeah, that's good. Yeah. When you at the end you mentioned about you have some analytical solution, but in principle, if you have done a faithful monocolor implementation, they should be the same, right? At the end.
In principle, of course, there are always approximation, even the analytical approach. It is really that when you satisfy this. For example, we can first verify the implementation with some like a arbitrarily large separation of scale to make sure. For example, I think one thing that we need to verify is the scale setting. Whether the scale should be chosen at KT or virtuality, and I think that can be fixed by this comparison. And we can also get understand of how much uncertainty it may cost.
Well, hopefully we'll find a way to separate these two different scales by looking at different kind of region of final observers. So we are working on it, right?
Actually, if you look at light nucleus, for example, if you have a way to trigger centrality in in electron-lead collisions, there may be even some region that you can flip these two. So if that happens, then you have transport regions for jet evolution in the nucleus.
Sure. Okay.
Maybe one last dumb question. Can this like result be used to search for the saturation, gluon saturation?
No. It's still in the DIS limit.
Okay.
Yeah, it's not there's a sort of saturation physics implemented, but it's not what you consider the deeply saturated limit region of the nuclear. And that's very different when you want to go to very small x, so there's a lot of glue.
Okay.
Yeah. But if you have any saturation measurement, it should include this, right? It should include this.
So here you do have the at least in this approach, you do need the unintegrated gluon distribution, right?
Yeah, you need the unintegrated distribution.
So somehow it's entering quite indirectly in the form of the transport parameter, but it's not the same saturation scale people discuss at the small x.
Oh.
Yeah, just a naive question. I'm not very sure because if we reach, so everything here is kind of analytic for the RG part. I'm not sure it's possible to calculate something non-interpretatively using lattice stuff for these regions where you cannot.
Okay, so for example, the good thing about separation of scale is that when you do numerical simulations, you can set up a problem with a single scale.
Yeah.
For example, you don't have to simulate large Q-square events on lattice. Well, this evolution will take you there. But for some of the inputs, definitely, if there are, for example, lattice or effective models, can provide.
Okay. So for now, it's kind of separated, and you don't need to bother that.
Yeah, you need a cut, not just a cutoff over there. But eventually, you need to consider what gives you this cutoff on physics around it. That, for example, where should you stop this evolution exactly? And especially when you look at transverse momentum distributions, what gives you those very soft momentum kicks that will be not available in this?
I'm just wondering a kind of a transition region where you can connect these two and connect the perturbative or RG revolution region with the non-perturbative region, then you can cover the whole thing. But I just naive thinking, but I'm not sure.
And actually here, you already see the necessity of non-perturbative physics, right? Without hadronic interactions, you will not be able to explain why antiproton is so different here. Right here, if you compute z times zh times e over L, when zh is small, then it becomes non-perturbative, right? And then, of course, in this region, hadronic physics and maybe other NP physics will come into play.
Okay.
Okay, I think
Thank you.